Hello, and welcome to another video in this series as we learn Prolog together. Right now we're in the middle of a few videos exploring meta-programming and creating a meta-interpreter for Prolog. This is the third one actually, so the previous ones introduced the idea of meta-programming, and in the very first video we built what was probably the most minimal meta-interpreter possible probably. In the last video we extended it a little bit to work with programs that are deductive. So this was actually the program that we developed last time, where we had a simple fact or set of simple facts and rules that were also quite simple. So a rule head and one property in the body, a rule head and a property in the body. What we wanted to do last time was to follow the deductive chain, as it were. So our meta-interpreter could prove or disprove queries which required life form to be linked to animal, and animal to be linked to mammal, and mammal to be linked to basic facts about a cat and dog. So our aim was to get deduction working. Today we're going to extend our meta-interpreter a little bit so that it can cope with programs that have more than one property in the body of a rule. So you can see here there's an empty body here, which is essentially the same as saying true, if you remember that. That's something we've talked about a few times. But the most complex rules are in the previous video were nothing more complex than a simple property is true if another simple property is true. There wasn't a set of properties like 1, 2 and so on. There wasn't that. So today we're going to extend our meta-interpreter. So this is a program which you might remember from a much earlier video where we were exploring recursion, and it's the property same, and you might remember that we developed the property same to decide whether to define actually whether two lists are the same or not. So we had a list and a second list, and the property is true if those lists are the same. And it was, when we were exploring how recursion worked. And you can see here, just as a brief reminder, how the definition compares the head of the two lists, and if they are the same, then we're almost there. But in addition to the heads being the same, the tails have to be the same, and the tail uses the same property, same. So it's recursive, and if you keep comparing the tails, chopping off the heads, you end up with two empty lists. If the two lists are unequal in length, then you don't end up with two empty lists. And if you have two lists that are the same length but have contents that are different, then this assertion will fail. That was just a brief kind of reminder of how this works. There's an entire video dedicated to developing and explaining that program, so do go back and have a look. But you can see there's new challenges if you want to meta-interpret this program. And the first one is that we now have a property where the body has two parts, two properties that have to be true. We could have extended it more, but it's more than the one that we looked at last time. So we have to find a way to work with that. And there's something in the middle here, which is, remember, it looks like an equal sign, but actually we interpret it as unification. So how do we meta-interpret unification? So we'll talk about that today as well. The code is online on GitHub. I've deliberately deleted 2 lines here because I want to talk about them before I fill them back in. The code that you can see for the meta-interpreter is the same as what we've developed previously. So you can see there's proving true is just true and there's a cut to stop it backtracking, and that was discussed in the last video. And to prove a query, we look for rules that either match the head, and then we look at the body and try to prove the body, and that's recursive. But as we do so, we also print to the screen what the head and body are, and this kind of right to left implication as a way of explaining the decision whether something is true or false. So again, we did all that last time, so if you need a refresher, do go back. But I've deliberately kind of blocked out any additions to our meta-interpreter until we've talked about them. So how would we work with rules that have more than one part to the body? Well, let's walk through this as if we were just going to apply this last video's meta-interpreter. If we wanted to prove something that's, two lists are the same, we'd use prove like we did before. So we might do something like prove, and then we'd say are two lists the same, and we might say something like 1, 2, 3 and 1, 2, 3 as the two lists. So this would be the parameter that's passed to prove, that's h. We are then looking for a clause that matches that query, same as last time, and we would find one, this one here. This one doesn't match because the two lists aren't empty. If this was a variable, then it might match, but it's this is concrete, so this one matches, but that doesn't. So this is the one that matches, and then B, if you remember, is unified with the body of the matching rule. So B should become the whole thing. Well, we've not seen that yet, but that is what happens. So that's the answer to the question: how do we cope with, how do we work with rules that have more than one part? So previously B would be just the single property, but now it will become the multiple one. Let's try that. Let's look at clause and see what B is unified with. So that's the H here, and that's the B. So let's see what that finds. Yep. So B is this thing here, and it's actually instantiated those variables h1, h2, t1, t2 with the actual content because we've provided it. So 1 equals 1 and same. So this is a list. So the body B, the variable B, is unified with a collection of Prolog properties. So that's new. We've not seen that before. It's almost like a list of Prolog properties. So with a list we'd have square brackets, but we've got round brackets, and you may have seen before that round brackets is a way of grouping together Prolog code. So you can have Prolog statement A like true, you might have another one like that, might have that, and you can group that together as one. I'm not sure what will happen if we run that. It'd be false, yeah, because of the false. Let's say A equals 1. Yep, so that all runs. Great. So when we had lists, we could traverse them by chopping off the head. Do you remember something like this? So if we had a list equals A, B, C, that's a list of 3 items, and we could unify that with HT, and that would become A, and that would become B, comma C. We did this quite early on, and we can do this recursively if we want to work through a list. So how do we work through a collection of Prolog properties, like true, something like this? If these are round brackets, it means it's not a list in this sense. It's not a Prolog list. It's just a grouping, a collection of Prolog properties. Well, actually, you can. There is a way to do that. So let's have a look to see how you might do that. So let me change color. So if I unify this with not square brackets, but round brackets, and call that A, comma B, as you'd probably expect, A becomes true, this one here, and B is the collection of the remaining Prolog, so that becomes false. So it's very analogous to how we work with lists and chop them up. Let's actually try that hands-on. So as you can see here, I've made up a test rule just here, just for the purposes of doing this, and I've got a rule with 3 parts, 1, 2 and 3. They're not really meaningful here, they're just for the purposes of this testing. So if I say clause test x, comma b, that should return the body of this rule. Let's try it. Yep, 1, 2, 3, and we can see it's contained in round brackets. So that's what B is. Now if we unify B with, let's call it head H1, tail 1. That's more familiar with how we've been using those names. Let's see. Yep, so B was this entire thing here, wrapped in round brackets, so it's a collection of Prolog properties. And then we've unified B with H1 T1 using round brackets, not square brackets. So we've chopped off the head, that's 1x, and the tail is 2 and 3, again wrapped in round brackets. So we could unify that with say H2 T2 to kind of further chop that up. Yep, so H2 is now 2 and T2 is 3. Now this is the only difference between lists and these collections of Prolog. So if this was a list, we'd have a list of one item. There would still be square brackets around that, but it won't cause us problems in terms of the Meta-Interpeter. So just to summarize that, just as we can work through a list with square brackets by using unification, H vertical bar T, this thing here, we can work with a sequence of Prolog properties by working through the chopping off the head at a time using this kind of construct. So it's very analogous. So that will be helpful. So what do we do then with our Prolog in Meta-Interpeter? Because we can't just say prove B, because that itself will be a collection of Prolog properties, and that wouldn't make sense. We have to kind of chop them up. So we need to deconstruct them in the way that we've just seen. So as it stands, if we ran this Meta-Interpeter against this program, then B, for this property the same, would have these two properties in one collection. In fact, let's do that directly. Clause same 1, 2, 3, 1, 2, 3, B. Oops, I made a typo somewhere. I missed out the bracket there. Yep, so B would be this collection of Prolog contained in round brackets. So to prove that, we can't do that directly, but what we can do is create a rule in our Prolog Meta-Interpeter that kind of chops that up in the way that we've just seen. So if we say prove, and the matching, the pattern matching as it were, is true rules, say x comma y. So that, remember we've just done that, we've said AB here, we could call that AB or XY. Let's do AB because that's what we've just done for consistency. And so what do we do here? Well, the A will be the head of that list of Prolog. So we can prove that, prove A. And what do we do with the tail? Well, we prove that too. And if it's if that itself is also a list, it will match this again. So it's recursive. If that feels complicated, let's draw a picture. So if our sequence of Prologs is, let's say, true, cut, false, and we did a clause match, and that's what the B came out as. If we wanted to prove B, B would be this thing here. So we need a rule that matches that. And because it's a list that could be longer, you know, it could have true here as well, or some other property like same or happy or tasty. We need to deconstruct it, we need to chop the head off, and we're working left to right, remember, so that the head is the left part of that list or sequence. Then that's how that works for us. So we want to match that like that. So we want to prove something of this construction. So we say prove A, comma prove B. If I'd used X, Y, it might be clearer here, so we don't miss up with conflict there. So here B is this, and then X becomes the first bit, so we just prove the first property. So this will always be one property that is provable or disprovable. And then this becomes the rest of it. And because we're using prove, we can go back recursively, and then the next time it'll chop the head of the sequence, so this one will be that, and we can just prove that in the normal way, and so on and so on. So I hope that's helpful to see it kind of more visually like that. And you can see again, we've taught quite a lot, we've explained quite a lot, done a lot of thinking, but the resulting Prolog is quite small there. Let's try and jump ahead a little bit and try and run this Meta-Interpeter. So let's try and prove that two lists are the same. 1, 2, 3, 1, 2, 3. Let's try and prove that. Just put those brackets in the right place. It won't work fully because you can tell that there's a little bit of code that's still left to be developed, but it'll be educational. Okay, so it stumbled in the same way that we stumbled last time when Prolog complained that we didn't have permission to access private procedure. Last time it was true. We were trying to use clause on true, and this time we're trying to use clause on what looks like =2. What is =2? Well, looking at our program, it must be this, because there's nothing else that looks like it at all. In fact, it's the unification symbol, the one that looks like an equal sign. It doesn't know how to kind of get the body of that because it's a built-in. So we need a way to actually write a rule to handle that, so it doesn't have to be we don't have to kind of try and find the body of that built-in. So what is this equal /2? Well, /2 means it takes two parameters. Does this take two parameters? Let's hover over it. Yeah, it seems to suggest equal /2 ISO. That's the ISO standard, the international standard for Prolog. And it says unified term 1 with term 2. Yeah, so why does that look like it's something that takes two parameters in brackets? So if we look at a property like same x, y, that had an arity of 2, if you remember. Arity means how many parameters it takes. That one and that one. If we had, from last time, we might have had mammal, cat or dog or eggs. That's an arity of 1. Why is Prolog talking about equals with an arity of 2? Does it take two parameters like x and y? This does not look like how we've used the equals sign for unification. Actually, this is correct. This thing is an operator with an arity of 2, and it does take two parameters to unify them, and in fact it can be used in this form. This form, xy, is the same as x equals y. This is actually for our convenience, and this is actually the standard Prolog form. So when we see x equals y, or a is b, those kinds of things where there's something in between two parameters, that's called an infix form. Infix. But it's actually, this is the standard form, and if you want to, you can say is a b. Let's just try it for a bit of fun. Let's just try, first let's try x equals 3, just as we expect, x unifies with 3. But if we try equals x comma 3, does that work in the same way? Yep, it does. Just check 4. Yep, that does. So this is the Prolog standard form, and the form we use is just purely for our convenience, not for Prolog's convenience, the infix form, because we're used to it. You know, we're used to sort of saying x equals 3. Let's try is. Y is 5 plus 3. That's the arithmetic. And if we say is y comma, that should also work. Y is 8. If I just change that, it should be 10. There you go. So that's just to be aware of. You might see, you know, in some of the courses or textbooks, some of the traditional operators that we're used to, like is and equals, referred to with an arity, and that's just the explanation for that. So our prover choked on this equals, and the reason the error popped up is because as it worked through interpreting the program for same, it hit this. So to prove this thing, it didn't know how, so it called clause on it, on the property, and the property is equals. So we need a way to handle that, and we do that in the same way that we did true. So last time we hit the same problem with true. We just need to handle it before it gets to this point and it fails. So we need to find a way of handling A equals B or X equals Y. And how do we do that? How do we execute the code for a property that's being meta-interpreted of that form, H1 is H2 or A equals B? Well, we can just do it like this. That might sound wrong, or it might be a tautology, but actually it's correct, because this is true if this is true. So to prove that we want to prove A equals B is true, if A actually can unify with B, if it can, then we prove that A can be unified with B. So let's say that, because it does sound funny. If A can be unified with B, then we can prove that A can be unified with B. That sounds like a head twister, and it is, because that's what metaprogramming is. It's kind of taking a step back and writing Prolog that'll run Prolog. So this Prolog is running this Prolog. Right, let's try our query again. So we want to prove that these two lists are the same, and hopefully there won't be any errors now. Our meta-interpreter that's extended now, and it can cope with programs that contain unification, and it can work with programs where the rules can have more than one part, more than one property. Hopefully this will be successful. And what do we expect when it works? Well, we expect this to be true, 1 2 3 1 2 3, the two lists are the same, but we expect it to print out an explanation. So that'll be the exciting part. So let's run that and see. Great, that worked. Let's talk through or read what it's printed out. It's saying the two lists 1 2 3 1 2 3 are the same because 1 equals 1, the heads are the same, and the tails are the same. 2 3 and 2 3 are the same. And this is true because 2 equals 2, the heads are the same, and then a list of 3 and 3 are the same. And that is true because 3 equals 3 and the two empty lists are the same. And the two empty lists are the same because it's just true as a fact over here. So that's quite cool. So our ability to print out successfully kind of matching rules as an explanation is really handy, particularly when you have a proof that requires several steps, like a recursive one. So our meta-interpreter is recursive now, at least here, and here. But now we can work with programs that are recursive as well. So same will call same, and our meta-interpreter can handle that without any additional thinking, because all we needed to do was the ability to work with multiple properties in a rule. So that's fantastic. Let's just try it with another one. Cat, dog, banana. Just to illustrate that. Cat, dog, banana. Let's run that. There we go. Let's reduce the text size a little bit. There, just so we can see that more clearly. So it's saying that cat, dog, banana are the same because cat equals cat, and the lists dog, banana are the same. And that's true because dog is dog, and the two lists containing banana are the same. And they are the same because banana equals banana, and the two empty lists are the same. And the two empty lists are the same. It's just true because it's stated as a fact. So that's quite cool. That's quite useful. our Meta-Interpeter, although it's only had 2 extra lines added to it, it's suddenly become a lot more powerful. It can now work with recursive programs and also rules with lots more than one property in the body of the rules. So it's becoming fairly general. It's not by any means, going to run all Prolog programs. That's not the object here. That's not what we're trying to do. But it's a great leap forward. There's lots of programs that can be run like this now. So that's quite an achievement, actually. I think it might not become apparent, but as you go away and think about it, the number of Prolog programs that this can now cope with has grown drastically. Have a go yourselves. Try other recursive programs that could work with this. Actually, just before I finish, I've made a little omission. I should have put a cut in the Meta-Interpeter just before, at the beginning of each of these handling rules, and that's to stop Prolog, the Meta-Interpeter, from backtracking. So it's matching the rule and attempting to implement the rule, so attempting to interpret A equals B by running A equals B. If that fails, we don't want to backtrack and try again and kind of work with the match the rest this more generic rule. So the pattern here is we have a cut at the beginning of each of these matching rules. You can see that with true, you can see that with A equals B, and you can see that with the one that dissects a sequence of Prolog code, and that would be the general pattern. Fantastic. So we'll finish there. Next time we're going to really challenge ourselves with probably the most difficult, I would say, topic or theme, and if it's something, feel free to skip it, but it's good to challenge ourselves sometimes, and that's how to interpret Prolog programs that might use the cut in the program. And just if you want to think ahead a little bit, remember the effects of the cut are not really trivial. The effects are felt kind of beyond the immediate place in the code. This stops backtracking, for example, which affects an entire line at least of Prolog, rather than just each part of a line. So if you think, how would we implement that in a Meta-Interpeter, that's not easy. So that will be quite stretching, but we'll do that next time. Fantastic. See you next time. Bye.